Hi guys, this is where we left off in our previous video. Well, let's just keep watching this. Pretty soon it'll be apparent what I'm making. In the lathe now, just smoothing it out, taking off as little as possible just to get it smooth. Now I'm parting off. I'm parting, spinning 1,000 RPM. Chip should be about 1/1000th of an inch thick. Going nicely. In the lathe now, facing off, going to a final thickness of 3/4 of an inch. And there they are, 4 of them. Here I've cobbled together a jig plate in order to hold the piece while I machine a pocket. Using my probing sequence, I probed the center of the hole, pre-drilled hole. Here we're moving very slowly to probe. That's because I use a solid probe and I don't want to bend it. I have drawn plans for a spring-loaded probe that you'll feel more comfortable with, especially after I switch to Mach 4, which has very nice probing sequences. Probe is at the center of the hole, so now I change my X and Y to zeros, and after that I move the X-axis 1/8 of an inch and zeroed the drows. This is my favorite way to set Z0. I use parallel, measure it, and enter that in the Z. So then the top of the stock is at 0, and I begin machining. I'm cutting slowly here because this piece is round and I'm not sure just how tightly this clamping system I cobbled together here will hold it. So I'm being conservative. I did make 4 blanks and I really only need 3 of these, but I don't want to press my luck. Here they are. What are they? You'll notice that the pockets are offset by 1/8 inch. And if you haven't already guessed, they are servo motor mounting plates, mounting on the eccentric, so that by twisting the servo in its mount, and here's the mount, you can tighten or loosen the belt that will be between the two spindles. To design this, I used Autodesk's Fusion 360. Here's a rendition of the whole plate, and this is the eccentric servo mount that we just showed you. It is a mostly free program, depends on your use. If you're using to make money, it's not free. The first thing I did, and this is a picture from Fusion 360, was to draw out all the critical sizes in just a two-dimensional sketch. And I was able to adjust the distance between the two spindles, which is that slightly angular measurement, to a little under a nominal number of teeth belt size. Here I'm starting to cut the stock that we're going to make the plate from. Facing the stock. The stock's a little bit over 3/4 of an inch, so you can take some off of both sides and still end up with 3/4 of an inch. After facing the stock, I want to set some work coordinates. I probed that upper right hand corner and set the position to 0, 0. And then I moved the machine 2 1/4 inches from each edge, changed the work coordinate from G54 to G55, then set that at 0, 0, repeated the same thing, moved over to the next coordinates, and set G56 to 0, 0. If you forget to set the Z0 for each coordinate, you could have a nasty little crash. Now these outside 3 holes here, they are on a circle, is concentric with the center of this, of course. In other words, we've got a great big circle here. And determining the diameter or radius of that circle is a bit difficult. I tried measuring between here and here on the actual part of the machine, and I got, depending on how I did, I got a couple different numbers. I got 1.605. Another measurement I got was 1.614, and I was going to try to make some test holes in a piece of sheet aluminum or in a piece of plastic and see what matched up the best. And then I remembered that I had some plastic, and so I thought, well, I'll draw one of these radiuses and hold it up against the hole and see if I hit the middle of all 3 holes. Well, I did that twice, and one of these numbers was too small and the other was too big. So then I got to thinking that, well, most of the measurements on this machine are metric. So I decided to try 41 millimeters, and lo and behold, when I did that, the lines, I don't know if you can see them on this piece of plastic, but it's actually got 3 lines on it, and the 41 millimeter radius hit the center of the holes exactly, so that was the radius I used. So what I did was I set the caliper on millimeters, turned it up to 41, tightened it there, and then I took a compass and set it to just fit inside there. Then I had a little center punch mark I made, and I just scribed the circle. And the metric circle matched right in the center of all 3 holes. Voila! Newfangled Wizards. The Newfangled Wizard screen starts with some job settings, and then some further size settings, and then you get to a screen. Now what I punched was circle, and the first 2 buttons down the bottom there are the direction you're going to go, and then you can mill inside, outside the circle, right on the circle, or make a pocket. You also have the Z settings, the top of the work, whether you're going to spiral down, the depth, and the depth of each cut. And then you get a picture of what the path is going to look like. Then you can save the G code or look at the G code. It's a pretty handy little program, and I use it a whole lot. Here's a look at the circle part of the program. You notice X and Y I have set at 0. They could be set at anything. Here I changed the number of holes to 6. I changed the start angle. Here I set it to 30. And of course you want the circle diameter in there. And then the Z settings over on the right there, the top of the work, the depth you're going to drill, and if you're going to peck, the size of the pecks. You can do various drilling cycles. If I go over here and eliminate the circle, you can see how the drill sequence is going to go. And it starts out and goes around counterclockwise to each location and drills the hole. Here you can see the machine making the final cut on one of the pockets that I prescribed in the Newfangled Wizard. If you don't have the Newfangled Wizard, I would advise you to download it and play with it. You can download a free trial. It won't give you the G code, but you can see what the toolpaths are going to look like, and you can see all the possibilities of the Newfangled Wizards. Fusion 360 is also a full cam program, and you can do all of this with that. I just find that for some simple things about like bolt circles and pockets, it seems to me faster and easier than using the full blown cam program. It's a matter of personal preference, I suppose. Here I'm making the tiny little pockets that amount to the counter bore for the 3 mounting holes that will hold the plate to the top of the Z-axis column. Here you're watching the finishing profile, the outside profile of the plate, which was programmed in Fusion 360. And then a little bit later, you'll see a chamfering bit, making a chamfer around the outside of the finished piece. That was also programmed, that path was also programmed in Fusion 360. It's a great little program, not a little program. It's a full-blown CAD CAM program, rivaling the most expensive out there. I modified this drill press a few years ago. I put a DC motor on it with a control board, a knob to control the speed, and I use it for a lot for tapping. Now, this hole is actually tapped already. This is an afterthought to show you how I did it. So when you get a close-up, if it looks like the hole's already tapped, that's because it is. Here's the chamfering cut. That's a 1/2-inch carbide chamfering bit, the first time it's been used. Part of the bearing set, the bearing pair, is going to sit down in this hole, and the rest of it will reside in the bearing cap. But in order to know how deep to make the pocket in the bearing cap, I need to know the exact depth of this pocket. Now, it's taken the old man a little bit long to read the mic, and that's because these depth micrometers read backwards from a regular micrometer. At least that's my excuse. Okay, that done, let's jump back to the full piece here. Here I'm probing the center of the thickness. I want to make a hole, drill a hole, and tap a hole. It's exactly in the middle. So there I am in the middle. I remove the lead, and then I'm going to take the probe out and start to machine what I need to do in that particular spot. You might be able to see some little black marks on this side. They're marks to tell me how far to go down with a counter bore, and then the lower mark is the middle. That's where I change from clearance hole to the tap size hole. Okay, now we're drilling the tap size hole, and after this, which I don't think I have a picture of, I'll drill the clearance hole. Here we're using the slitting saw, carbide tip slitting saw, to cut the slot, which will allow us to tighten up the circle around the servo plate. Sorry. I measured the depth of this pocket. Now you'll notice when the bearing is in there, it sticks up a little, and that is by design, so that the cap and the other bearing will be located by this bearing, perfectly concentric. I subtracted the depth of that hole from the thickness of two bearings, and then I machined this face right here so that the pocket was about 1/1000th of an inch less than the thickness of the two bearings, and that gave the outside bearing races a positive squeeze. So then it's just a matter of screwing them all together, and eventually we'll mount this on the column, and we'll have the bearing races clamped in place, controlling the thrust of the lead screw. And here we'll have the servo mounted, and with a single screw we can turn it on its eccentric and create tension on the belt of the two pulleys that will be on this side. A pulley there and a pulley there. The top of the lead screw, ball screw, has a nut that goes on top that squeezes together the inner races of the bearings. It's a spanner nut, and that's it. And it will stick down a little bit into a pocket and be difficult to tighten. So I decided I'd make a wrench. I didn't find any place that I could buy a wrench that would fit that, so I decided to make a wrench to be able to easily tighten that. This toolpath was created in Fusion 360, and I wanted to try out the adaptive clearing protocol, I guess you'd call it. And I think maybe I don't totally understand its use and what the advantages are and how to use it, because it created a rather complicated toolpath that's taking a very long time to cut. Eventually it does work out all right, and the tool fits the nut with just a little bit of filing to clear up the rough edges. You can see right there, fits great. Now, if you remember in the earlier videos, there was some question about how accurately I was able to measure some distances, and I decided that I was going to need a little bit of room to accommodate slightly moving the top plate in order that it line up with the lead screw perfectly. And so I drilled these holes, and that counter bore 50 thousandths oversize, so we could move the plate in any direction up to 25 thousandths, and I thought my error was probably no more than 10 thousandths at very most. So here we're looking at where this plate is going to go. It'll go right on the top, and we'll be able to adjust it a little bit, as I say. I'm not going to bolt it on right now. I need to do some heavy lifting here with the help of a little crane, I guess, and get the base up on the rollers, and then get the column up on top of the base, and then we can mount these new parts on top of the column. Thanks for watching, and I'll see you next time. Bye.